Welcome students for today's lecture on equilibrium of forces. I am Professor Sagar B from Civil Engineering Department, Angli Institute of Technology and Management. So today we will discuss about how the body remains in equilibrium and what are the constants in it and what are the equilibrium equations. So let us start. Let us start with the statement of equilibrium of forces. It is the state in which the forces applied on a body are in balance. The meaning of this is any body will be having some reactions, the body will have some forces applied on it. So, for an example, if a body is kept on a table, say if a ball is kept on a table, if it is in standstill position, though the ball will try to move downwards toward the center of the earth, but the table is holding it. That means what? The body is in equilibrium, so it is standing straight. Then let us see what are the forces and what are its components. So equilibrium force. Now what is the equilibrium force? It is nothing but the force which brings the body into equilibrium. Therefore, an equilibrium force is equal in magnitude and opposite in direction to the resultant of all other forces acting on a body. Equilibrium force is the force which brings the body into an equilibrium. So let us tell you with an example. So equilibrium in short is also defined as a force or a movement required to keep an object in an equilibrium. So the example is like this. Consider two forces F1 and F2. So this is the direction which they are going. So if you find the resultant for this, the resultant will be in this direction. So the resultant is given like this, resultant force. So this is the reaction of these two component forces, that is F1 and F2. So the resultant is acting in this direction. Then the equilibrium force will be the force which is not allowing for this resultant reaction to happen. That means it is equal and opposite. So I have demonstrated here. So the resultant of these two forces is this. So this is the resultant of force. So then what will be a equilibrium force? A force equal and opposite to the resultant force. So this is the equilibrium force. Hence we can say that it is a force which brings the body into an equilibrium. And in a more specific way, in a civil engineering term, equilibrium is defined as a force or a movement required to keep an object in an equilibrium. Now let us see what are the equations of equilibrium. So equations of equilibrium are the equations which will keep the body in equilibrium. For example, if I take a three-dimensional structure, so when a body is there, many number of forces are acting on it. But the equations of equilibrium are 6 for this case. For a three-dimensional structure, say let us say x, y and z, the equations of equilibrium are summation of f of x equal to 0, summation of f of y equal to 0, summation of f of z is equal to 0. That means what? All the forces summation is equal to 0, as well as the movement about all the directions are 0, that is summation of m of x, summation of m of y and summation of m of z. So we have in total 3 dimensions. So in all the 3 dimensions, the forces summation are 0 and the movement summation are 0. For an object to be in equilibrium for a 2-dimensional structure, say if I consider x and y only, then the equations of equilibrium are summation of f of x equal to 0, summation of f of y is equal to 0 and summation of movement is equal to 0. So f of x about the x direction summation of forces is equal to 0, summation of f of y is equal to 0 and the movement about any one point is 0. So this is the more overused because we are solving a numericals in elements of civil engineering and engineering mechanics of a 2D dimension. So moreover, we are going to use these equations of equilibrium. So for the equations of equilibrium for a 2D structure, the equations are summation of f of x equal to 0, summation of f of y is equal to 0 and summation of movement is equal to 0. Next, let us see how the equilibrium equations are there for the systems. Now let us discuss about equilibrium of coplanar concurrent force system. What do you mean by concurrent? Concurrent in the sense all the forces are acting at a single point. And coplanar means it is acting in a same plane. So the coplanar concurrent force system means the forces are acting at a same point and in the same plane. So let us see how it is described. The resultant of a concurrent force system is a force acting through the point of concurrence of the given force system. That means what? The resultant of a concurrent force system will act from the same point where the point of concurrence is there. The condition for equilibrium is that the resultant must be a 0. So let us see, these are the 5 forces acting at a point O. So this is concurrent and acting in the same plane. So the equations of equilibrium for these are summation of f of x equal to 0 and summation of f of y is equal to 0. So remember, the equations of equilibrium for a coplanar concurrent force system is summation of f of x is equal to 0 and summation of f of y is equal to 0. Now next, we shall discuss about equilibrium of coplanar non-concurrent force system. So what do you mean by non-concurrent? Non-concurrent means there are a number of forces which are not acting at a single point, and coplanar means they are acting in the same plane. So let us see. The coplanar non-concurrent force system can be reduced to a resultant force and a couple and a moment. I have taken an example. Say this is a beam and these are the forces acting on the beam, that is F1, F2 and F3, wherein the F1 and F3 are vertical forces and F2 is a inclined force. So they are acting in the same plane but they are not acting at a single point. That is called as coplanar non-concurrent force system. For such kind of an system, the conditions of coplanar non-concurrent for a system are summation of f of x equal to 0, summation of f of y is equal to 0 and summation of moment is equal to 0. So remember, whenever we have a coplanar non-concurrent force system, for this system, for the forces to be in equilibrium, these are the 3 equations of equilibrium. Summation f of x equal to 0, summation f of y is equal to 0 and summation of moment is equal to 0. Now let us discuss about free body diagram. Now what is a free body diagram? The body has a number of applied forces. There may be external force applied on the body. All these forces are acting at some point in the object. If I take a circular object and if the forces are acting on the object, then the forces are concentrated towards the center. Likewise, I can say that all the forces are gathering, whatever the forces may be, that may be internal self weight, that may be external reaction or external reaction provided by some object, or it may be an applied force also. They will be acting at the CG of the body. So let us see the definition. The free body diagram is the isolated diagram of an object or a system of object or any point in the system in which all forces and couple moments acting on it are shown, including the supporting reactions. We can also say that when objects are supported by some supporting mechanism, the supporting mechanism exerts a force or a couple moment on the object which tries to restrict the motion of the object. That's what it is. These forces or couple movements which oppose the restriction of the motion by the objects are called as support reaction. Let us discuss with few of the different diagrams or bodies on which the forces are acting. So free body diagram for different bodies. So let us see. So the first example is a cantilever beam. You can see here the force F1 is acting at the end B and F2 at some point in the beam and there is a mass. So if I happen to draw a free body diagram for this, so the forces will act at the same points. The cantilever beam has its own self weight. So where it will act? It will act at the CG of the body. So CG lies here. From the CG it will try to travel downwards towards the CG of the earth. So self weight going downwards W. And this is the support reaction. So this is the fixed condition. So for fixed condition, what all we will be having? We will be having 3 components, that is force along a reaction along vertical, reaction along horizontal, and a moment. So this is a free body diagram for the cantilever beam. Now let us take a second example. These are the two spheres in the trough. They are placed. Now you can see there are two spheres, one is bigger one and one is a smaller one. So let us see. Now you can see here the many points of contact. The sphere A is in contact with the vertical surface of the trough as well as the horizontal surface of the trough, as well as this small body is even in the contact with the sphere B. And the sphere P is in contact with the vertical side of the trough and with respect to sphere A. Let us draw the free body diagram for this A. So what will happen? This is the CG of the point. So there is a reaction between A and B which will go towards this point, and the reaction between the sphere B and the vertical trough. So here it is explained. So what is happening? This sphere has its own self weight which will act downward, and this reaction which is caused in between A and B, so the reaction is traveling towards the point B, that is the CG of the point B. And this is the reaction between the sphere and the vertical trough. So this will be acting perpendicular to the wall. So you can see these are the reaction how it is generated. Now this in turn is putting some weight on the sphere A. So even this will produce a reaction at A as well as a vertical reaction at this point and a horizontal reaction at this point. So in the sphere A, we have 3 points of contact, that is 1, 2 and 3. So you will have 3 reactions here, R1 along this perpendicular, R2 along this perpendicular to this surface, and this one with respect to the sphere B. So these are the reaction and its self weight. So this is how the free body diagram for these spheres are there. Now let us take the next example. Ball resting on a surface. This is a ball resting on a surface. You can see this is in contact with this. So we have two reactions only. One is the reaction due to the sphere A and the surface and the self weight. So self weight is acting downwards and this is the reaction how it is produced. Now let us see a example of box on the inclined surface. So this is how the box on the inclined surface is there. So obviously this will also have a self weight. So self weight will act downwards, and this is how the reaction, it should be perpendicular to this surface, contact surface. So the reaction is developed. Similarly, we have n number of examples here. Let us take this as an example. So you can see a sphere is there here and it is attached through a string. So this will provide a tensile force in this, and the contact between this sphere C and the wall B is given by the reaction, and this sphere has its own self weight, that is W. Let us say this is a single sphere which is supported by the two walls. So you can see the self weight will act downwards and there is a contact between the sphere and the wall here and here. So you will have a reaction here, that is in the perpendicular direction. So this is the reaction Ra on this component, self weight acting downwards, and this is the reaction which is going through the connection between the sphere and the wall B. So this is how the free body diagrams are to be drawn. So these are the very important concepts. We need to know how to draw the free body diagrams for the given numerical or for the given object and for the objects with the applied forces. So this is for the today's lecture. So let us see how the components takes place. So I thank you all. So all students, please be safe and stay home. Thank you.